Toru, what's going on?
Hello.
Hello. It's just me and you today?
Yeah, looks like it.
Interesting. Well, how you doing? I guess it's good to know each other.
I'm doing okay. I couldn't make it to yesterday's class though because I had an exam at the same time.
Totally fine. Don't worry about it. It's asynchronous. Nothing required. What class was it?
It was a multi-variable.
Who's your instructor for that?
Kasabian? Kasabian? Something like that.
You think I know all the math instructors here, but I have no idea. How'd it go?
I went pretty well. Yeah, I got a 19 out of 19. So that's, pretty good.
That is the Frenchest thing I've ever heard. Have you heard that apparently the French, they don't like we base our grade system off 100. They base it off 20.
Oh yeah.
I've heard, I don't know if this is true, I've heard that the highest grade you can get to 19, which
Oh,
because no one's perfect,
right.
right? And so even for like a math class, the highest you get to 19 out of 20. So a 19 out of 20 is 100%. So their 100% is whatever weird fraction 19 out of 20 is. Which doesn't make a difference, but it doesn't make any sense at all because the whole point of math, right, is that we live in an imperfect world, but we can abstract it to a perfect platonic conception of the world, and then you can actually be perfect. See, they don't get it. I don't understand. I don't understand how they possibly made Descartes and Fermat some of the greatest mathematicians of all time. But anyway, how's it going, everybody? Toru's doing all right. Safi, you chilling?
Hell yeah.
Good to hear it. Anything interesting happened between Monday and Tuesday?
Ravens lost.
Is that really interesting, though?
Yeah, Lamar's a beast.
Oh, it's true.
I'm surprised.
Yeah.
Oh, VT1.
See, Toro wasn't here for yesterday's conversation. Apparently, you, Toro, were the only person that saw that game. Yeah.
It was like the first half was kind of like a stomp though. It was like 20 something and I was like, okay, this game is over. And then I
Yeah,
stopped watching.
that's one of those where it's like, I want that to happen until it does happen, then it's kind of boring. You know?
Right.
Yeah.
Yeah.
It's like it's kind of like I want my thesis, and you want everything in your life to be easy, but then if it's too easy, it's like, well, where's the excitement in that? But speaking of excitement and things not being too easy, let's talk about some discrete math. Who's ready?
I hope so.
There we go. That's all I needed. Okay. I feel like Simon speaks to the whole class. By the way, there is a review session tonight from 5 to 6:30. So if you guys want to come by and hang out and ask all the burning questions you ever had, come on and do it. But anyway, today we are continuing our conversation. We're continuing section 4.1, and we'll probably dabble a little bit in a 4.2. 4.1 and 4.2 are like the same things. 4.2 is just like a slightly advanced 4.1. But anyway, I just put these section numbers here for your convenience, although I hate them because math does not break down in convenient little sections. It's just one giant blob of awesomeness. So it's hard to tell when one part ends and another begins. There is no really beginning and end of subjects. They all kind of blend together. And so, yeah, but anyway, the real thing we're doing today is talking about mathematical proofs. We did our second proof last time, proving that the square of any odd number is odd. And before that, we proved that adding any two evens together will give you an even number. So we've done two proofs so far. And I have, how many do we have today? We have 1, 2, 3, 4, 5, 6. We have 7 possible proofs today. We'll see which ones we do, how far we get. But anyway, let's just start out by reminding ourselves what we're doing. So really, every statement we can make, or I should say every quantified statement is either a universal statement, otherwise known as a for all statement, or is an existential statement, otherwise known as there exists statement, like a there exists, something like that, right? Even the ones that look weird, like even the ones that look like, hey, for all x and d, there exists a y and c such that like p of x, y. Even this is really just a for all statement where the predicate happens to be a statement that's a there exists statement under the hood. But it really is a for all statement. Right. And no matter what we do, I mean, like we only really showed examples in class with two quantifiers, but there's no reason you couldn't have a for all x and z, there exists a y and the real numbers such that for all c and the rational numbers, blah, blah, something happens, right? There's no reason you couldn't have that. This statement would be a for all statement. Just the first one kind of dictates what you're saying. You're saying for all x in the integers, something happens. So it's a for all statement. So we have for all or there exists statements. So, and then every statement in math, theoretically, is going to be true or false. Now, I say theoretically for some very, very interesting reasons that I hope we'll talk about, like the very last day, or in a fun class where we talk about all the math theory and all this high-level stuff. I think is fun. But every statement in math is either, just the way you can think about it now is that every statement in math is either true or false. There are some very particular statements that are actually neither true or false, depending how you look at it, but they're definitely not going to be both. So the point is, you're either going to try to disprove or prove something. And so to prove, let's do existential first. Or let's do universal first. Universal statement. So to prove a universal statement, we must show that to prove a universal statement such as for all x and d, p of x, right? Because all universal statements really have this form no matter what p of x is. To prove a universal statement like this, must show that p of x is true for any x in d you plug in. Who's got, and then what's one way we did that?
For finite domains, you can use the method of exhaustion.
Exactly, Safa. Could not have said it better myself. So one option to try to prove this is method of exhaustion. So I'll say proof methods. We had method of exhaustion. And this works for finite domains. So theoretically, for finite domains, you could always use method of exhaustion if you had enough time, right? We've been over that before. Another method is called direct proof. Let's just get right to it, right? No reason to beat around the bush with this proof. Direct proof. And that's the method that we used in the last two classes to prove that the sum of any two even numbers is even, and to prove that every odd number squared is odd. And direct proof, it always goes like this. It always has this form. So if we're trying to prove for all x and d, p of x is true, for direct proof, what you do is you let x be an arbitrary but particular element of D. Then show that the property of X and D, or maybe I should then argue that the property of X and D logically leads to X having the property that P of X is true. So we've kind of been over this before. This is called direct proof. So what you do is you let X be an arbitrary but particular element of D, then argue that the property of X and D logically leads that the property leads to X having the property that P of X is true, right? Then if P of X is true for any X in D, P of X is true for every X in D. Proof done. And that last line is a kind of subtle distinction, right? But the idea is we're going to let X be any arbitrary but particular element of D. Now, what we mean by arbitrary but particular, what arbitrary means, arbitrary, that just means that it's just any old element in D. We can't assume anything about it. So for example, in our odd number proof, right, where we prove that the square of any odd number is also odd, we couldn't assume, we started that off by saying like, let n be a particular but arbitrary odd number. But we couldn't assume anything else about it. We couldn't assume that this odd number, n was a prime. We couldn't assume it was a multiple of 3, even though some odd numbers are prime and some odd numbers are multiples of 3. But the point is it's arbitrary. So since not every odd number is a prime, and since not every odd number is a multiple of 3, we can't assume anything about it. It's just any old bland odd number, nothing special about it. That's what arbitrary means. Particular means that it's a particular one. That even though it's any old bland number, we don't know anything about it, it is one number. So we can't kind of switch back and forth and say like, oh, it's even now and then it's odd or something like that. It's one particular number, but it's an arbitrary number. We still don't know anything about it. And this will make more sense to be doing more examples. And then we argue, so we pick this arbitrary particular X and D, and then we argue that the property of X and D logically leads to X having the property that P of X is true. And I use the word argue here. I changed it from show to argue because we really are doing like an argument. Like remember we had arguments, we had like the modus ponens, modus tollens, we're doing that. We really are kind of doing those kind of arguments, except we're not going to point them out. We're not going to label them. We could, but we're not going to make everything easier to read and stuff. But we really are doing arguments. Like every logical step you take, like saying like this leads to this, should in your mind kind of be supported by some argument. For example, like if you know that this particular number X is either even, if you know that X is even or odd, and you know X is not odd, well then X has to be even, right? And that's by elimination, right? That's that you can make that logical step because we know there's an argument that supports it. Things like that. And then anyway, this last step right here is subtle. So once you've proven that for any X in the domain, P of X is true, well, if it works for any of them, it's got to work for all of them, right? Does that make sense? Like if any Virginia Tech Hokies player is a beast, that means every Virginia Tech Hokie player is a beast. You can't find a single one that's not a beast. That's a true statement. So, any questions about this? Then let's do an example. Cool. Actually, before we do an example, let's finish this conversation right here. So I was saying that either universal statement or the existential statement, right? Universal statement to prove true, we need to prove it worked for all of them, and we can do that by method of exhaustion or direct proof, which we'll do in a second. To prove false or to disprove, how do you disprove an existential statement?
Find a counterexample.
Find a counterexample. So to disprove for all x and d, p of x, find an x and d such that not p of x. That's all. And I've kind of been treating this as different things. Like I kind of been treating like proving universal statement, disproving universal statement, proving existential, disproving existential. They're really the same thing, right? Because when we're disproving something is the same thing. Disproving is same as proving the negation. Right? If you're saying something's false, something's not true, that means its negation is true. So disproving for all x and d p of x is the same as proving the negation of this, which is an existential statement. There exists an x and d such that not p of x, right? And how do you prove an existential statement?
Find one example where it works.
Find one example where it works, right? So that's why we have this relationship between disproving universal statements is the same as proving existential statements. Because disproving universal statement is proving its negation, which is an existential statement. So yeah, so to disprove, you find a counterexample because that proves the negation. Make sense? All right. Now, existential statements, we just kind of talked about it, but it's the exact same setup, but the opposite. For existential statements, so let's say the statement is, there exists an x and d such that p of x. To prove, use say to prove, find counterexample. Or sorry, just find regular example. So to prove, find example where it works. Find example that works. To disprove, show that p of x is false, or show that not p of x is true. Oh, it's not p of x being false for every x and d. Because remember, the negation of this there exists statement is for all x and d, we don't have p of x, the negation of p of x. So to disprove, we need to show that p of x must be false for every x and d. The opposite of there existing one x and d where p of x works is for every x and d, p of x won't work. And we can do this, and we can use method of exhaustion if D finite or direct proof if D finite or infinite. So these are the four options. You prove a universal statement with method of exhaustion or direct proof, and you disprove with finding an example. You prove an existential statement by finding an example, and you disprove by using method of exhaustion or direct proof. And that should just make sense, I hope. And by the way, direct proof can be used on a lot more, can be used on finite domains. And it oftentimes should be. Direct proof is way easier and way better than method of exhaustion. Method of exhaustion goes through and checks every statement. Direct proof just checks properties, which is a lot easier. So you should almost always use direct proof. You might always use method of exhaustion if your proof only involves like a couple of things. Like if your domain is just 2 things, maybe it's easier to check both things. But once it gets more, once it's like even 10 things, it's a lot easier to use a direct proof than to check all 10. Okay, any questions? Then that is the obligatory kind of boring definition stuff we have to get out of the way. Let's prove some crap. This is gonna be fun. So, the first thing I want to prove or disprove is, let's make a claim here. So my claim is that n squared plus n is even for all integer n. Now let's go ahead and write that all nice and formally real quick. How would you write this statement formally? First of all, is it an existential or for all statement?
Universal.
Oh, fancy words, Safa. Good job for being formal. So, what? For all n and what?
Even integers or
No, for all integer n, no.
For all integer n, right? So we're saying that n squared plus n is even for all integer n. So even or odd integers, this should work. Right? So even is describing what the result of n squared plus n will be, not what n is. So for all n in the integers, n squared plus n is even. It's formal. I can do better for all. And I'll give it a black tie because it's formal. There we go. Very nice. So yes, so here's the claim. We always write it formally. It's a really good idea of going on. What do you guys think? Let's do an aside. And aside is just scratch work. It's a fancy name for scratch work. Let's do some scratch work. Do you guys think this is true or false? No idea? Well, let's do some examples, right? Someone pick an integer. Give me any integer.
1.
Oh, okay, we have a chat. What about 0? Let's try 0. Good integer, Justice, one of the best. 0 squared plus 0 equals 0. And 0 is even. Why is it even? It's even because it equals 2 times 0, which is the definition of being even. 2 times some integer. So it works for 0. Who's got another integer? Let's try something else. Come on. This is the fun part of class. Try to mess this up. Try to find something. 5. I like it, Georgia. 5 squared plus 5 is 25 plus 5. 30, even number. Why? Because it's 2 times 15. And 15 is an integer. It works for 2. Why not? Let's do something weird. Let's try a big one. Let's see if it fails. Let's try like, okay, I don't know that many squares. So let's try, let's see, 101 squared plus 101. What's that going to be? 101, that's 100 plus 1 squared plus 101, which is going to be 10,000 plus 200 plus 1 plus 101, which is going to be 10,000 plus 301, 10,000, oh, plus 1, I forgot the 1. So plus 201 plus 101, it's going to be 10,302, which is even. Or you can use a calculator. The point is, we're getting a lot of even numbers here, right? So maybe it's true. Possibly your whole 2 to the n minus 1 thing on the homework has scarred you into not trusting examples, which is good. And examples aren't proofs, right? But maybe we can prove this. So let's think about it. Right, but before we start a proof, we should always kind of know why it might work. So let's look at n squared plus n. So a good problem-solving technique, right? Anytime you're trying to solve any problem, this goes way beyond this class. Right now we're learning life skills here, right? You thought I was teaching you math. I'm secretly teaching you life, even though like some of you are older than me. But the point is, a great problem-solving technique for anything in life is to simplify the problem, right? Like right now, we're trying to prove it for all integer n. Let's scale that back a little bit, right? What's maybe a more manageable goal than every integer? See, Benet says let your computer brute force it, but here's the problem, Benet. You can't brute force infinity, right? No chat after that, huh? Silence, Benet. Get very close. So what's a more manageable goal than proving this for all integers?
Like 1 to 100 or something? Or
We can do 1 to 100, but then we're gonna kind of, then that's where a computer can come in, right? But even if we prove for 1 to 100, we're still kind of infinitely many off. That's a good place to start, though. We could do that. Proving some property. What if instead of all integers n? I mean, we're trying to prove that n squared plus n is even. Maybe we look at, what if we just try for all integers n? Or for all even integers n. So that's probably going to come back. So let's see. What if n is even? Right? It's a little more manageable. If n's even, then there exists a k, and we don't have to be formal here, it's not proving anything. There exists a k such that n equals 2k, right? So n squared plus n is going to be 2k squared plus 2k, right? Which equals, let's see, this is going to be 4, or this will be 2 squared k squared plus 2k, which is 4k squared plus 2k. Does this look even?
yes.
Why? Yeah, why you say that, Toru?
Because multiplying anything by 4 or 2 will always give you an even number.
Yeah, exactly. Because the definition of being even is that you can be written as 2 times an integer. 2 times any, it's just some integer. And so what if we factor out 2 here? We can factor out 2, and we get 2 times k squared plus k, meaning it's even. Although we need to be a little bit careful here, right? Because you can factor 2 out of anything, right? Like 3 equals 2 times 1.5. So why is 3 not even, but I'm saying this number is even?
Because integers don't include half numbers.
Yeah,
The
exactly.
domain's
Because
already
the
been
thing
limited.
being multiplied here is not an integer. While this thing is going to be an integer. It's just 2 times an integer squared, because k is an integer. I should have said. And then that's going to be integer plus k is an integer. So it's all integers. It's going to stay in the family, right? So, so this is even. So if n is even, n squared plus n is going to be even, right? That wasn't that bad, right? So what do we have left?
The odds.
Odds, right? What if n is odd? Well, if n is odd, a definition of odd says that n equals 2k plus 1 for some k in z. So for some integer k, n equals 2k plus 1. Then n squared plus n, that's going to be 2k plus 1 squared plus 2k plus 1. Notice, however, though, we could FOIL this out, but by our thing we did last class, showing the square of any odd number is another odd number, this is going to be odd. So this is going to equal 2 times some c, I'll call it, plus 1, plus 2k plus 1. I'm not leaving all the steps in. We'll do that in the actual proof. And then this is going to be 2c plus 2k plus 2. Is this even?
Yep.
Yeah.
Yes.
Let's factor out that c plus k plus 1. These are all integers. This is an integer. Thus even. Boom. That's the idea. Does that make sense? And that's kind of neat. This is the idea to show that n squared plus n is even for all integer n. Let's not get too excited yet, because sometimes when you do scratch work, you don't show all of your work and you end up not being right. Sometimes people show a lot of work. Like there's one guy put out like a 400, 500, 600 page research paper, right? Proving something called the ABC conjecture, or something like that, I think. And anyway, it was really dense. Like only like a few people in the world could understand what he was even talking about. And even they had trouble checking it to see if he was right. It was taking them forever. And then while they were checking it, some guy came out with a counterexample and showed that actually what he was trying to prove correct was actually false. The point is, details matter. Don't be that guy. Put your work out in increments. But anyway, so let's move on with our proof. So the side just gives us the idea. Let's actually go through the mathematical proof. So proof. So we start out by saying let n be a particular but arbitrary integer. So now, here's the thing, right? We never work with integers or like full-blown integers. In our aside, we either worked with evens or odds. That's okay, right? Because every integer is either even or odd. So They form a partition is what it's called. So what I can say is note n is either even or odd. Proceed by division into cases. Uh-oh. I mean, what's the opposite of uh-oh? Yay. Oh, I don't know. The point is we talked about division into cases before, right? This is one of our argument forms. This is what I was talking about, where this kind of stuff is under the hood. So I'll say case 1, consider n even. So basically what we're doing right now is we're doing the division into cases argument form, where we have like for all n in z, right, n even or n odd. And then if we can show that n even implies n squared plus n even, and if we can show n odd implies n squared plus n odd, we can conclude by division into cases that n squared plus n is even. So that's what we're doing under the hood. So it all comes back. It's all there. I swear to you, it's all there. So we don't need to write any of that though. So case 1, consider n even. What we say if n is even? Then by definition of even, there exists a k and z such that n equals 2k, right? Then n squared plus n is going to equal 2k squared plus 2k by substitution, right? All it's saying is every step here we're going to justify, right? And so n squared plus n equals 2k squared plus 2k by substitution. We're justifying why we can do that. We can do that because n literally equals 2k, so we can substitute out for each other. All right. Actually, we don't need that. And then what's this going to equal? Well, and this is going to equal plus 2k. We're going to distribute that exponentiation by distributing exponent. Then this equals 4k squared plus 2k by evaluation. We're really writing every step. Here's evaluating 4k squared to get that. And this is going to equal 2 times 2k squared plus k by factoring. Right? So I've talked a long time. How do we end this proof? What do we like what do we do? We're so dang close for case 1 at least. How do we put it to bed?
We show that like an even is just anything, 2 times anything.
Exactly, right? So it's 2 times anything, but that anything has to be an integer, right? That's an important step we can't skip. Because if we just got to 2, like if we were doing a different proof, we got down to like, oh, x equals 2y, therefore x is even. Well, what if y was like 0.5 or something like that? What if y was pi? You know what I mean? We have to be a little careful, right? We're not leaving any stone unturned here. So, note that since 2 and k or in Z, and Z is closed under addition and multiplication, 2k squared plus k is in Z. Make sense? In the closed thing we talked about last time, that's just things you can assume, right? Like our few assumptions we started with is that the integers exist, we know what they are, and they're closed under addition and multiplication. Then we have that thus since 2k squared plus k is in Z, by definition, 2 times 2k squared plus k is even. This is where a lesser man would say boom shakalaka, but I'm just going to say any questions. So are we done?
No.
We still have a whole other case left, right?
Yeah.
Only
Yeah,
half
yeah.
of the integers.
We got half the integers, right? Which, hey, that's a decent percentage, all right? 50% is better than 0. If you just proved it for 100 integers, that would represent 0% of the integers. It's better than that, right? But anyway, yeah. So we've proven for half, right? So we've proven that part of the division into cases where if n is even, then you know that n squared plus n is even. Now I have to do the other part in division into cases. So in a normal proof, this will all be on one sheet of paper. So keep this in your sheet of paper. I'm going to pretend we're scrolling down and doing case 2 now. So let's do case 2. I'm going to breeze through this a little bit because we kind of know it. Because it's kind of the same. Case 2. Consider n odd. Then by definition, there exists a k in Z such that n equals 2k plus 1. Then n squared plus n is going to be 2k plus 1 squared plus 2k plus 1 by substitution, which then or I'll say actually to save us a little work and show how you do this, right? We can always use theorems that you can always use any theorem or anything we prove in class. So I'm going to use what we did in last class. So note by proof last class, the square of any odd is odd. Thus, n squared is odd. So by definition, there is some C and Z such that n squared equals 2c plus 1. Because to be odd, it means u equals 2 times 7 integer plus 1. Then n squared plus n equals 2c plus 1 plus 2k plus 1 by substitution. which then equals 2c plus 2k plus 2 by addition, or I'll say by evaluation, or by simplification. Here, simplification, evaluation, that all just means you're just doing some math, right? You're just adding two things together, that kind of thing. But then this equals 2 times c plus k plus 1 by factoring. And now we're in the same spot we were before, right? C plus k plus 1 is an integer. Why do we know c plus k plus 1 is an integer?
Is it because we know that c is an integer and we've
Yep.
defined k definitionally to be an integer for our,
Yep.
our base?
Exactly. We define c to be an integer. Right, where is it? Right here. C by definition is an integer. K by definition is an integer. 1 is an integer, right? That's the one thing we're sure of in this life. So then c plus k plus 1, since the integers are closed under addition, are integers. So then, I'll say note, since c, k, and 1, and z and z is closed under addition, c plus k plus 1 is then z. Therefore, 2 times c plus k plus 1 is even by definition. And we're so close. All we're going to put after this is one little line basically saying, and this closed out this case. Hence, since n squared plus n is even in all cases, n squared plus n is even for all integer n. Box, close it off. Done. Come on, people. Come on. I mean, right now, what we just did, right, is what we, like the same thing we did last time. We just proved something about infinitely many things. Well, I mean, there was kind of a lot of lines, but not infinitely many lines, right? This could fit on one sheet of loose leaf, right? We just proved this fact that we might have been taking for granted our whole lives. Like we might have thought it's true our whole lives, but we didn't actually know. This is the weird thing about math. It actually allows us to know, to be certain on a really, really deep level that we almost don't have in any other aspect of our lives. Any questions? Like this is almost inarguable in the sense that even if you had the best lawyers in the world trying to break apart this argument, they wouldn't really have anywhere to go. The only real place it has to go is say like, why are the integers closed under addition? Because that's our assumption. And then I could show them some sort of set theory proof that will come down to it, but then they go, why does that work? And I go, okay, because I guess we assume things exist. Like it has to come down to that kind of level. But anyway, any questions on this? All right. Well, that is a universal proof using the direct proof method. Pretty fun. We're using a lot. Note, by the way, that this level of detail I'm showing is expected in homeworks and tests and things like that. This won't be on your test on Wednesday, by the way. This is all stuff for this is all new stuff. But for the things going forward, this level of detail is kind of expected. You need to justify every step like that. You need to say that the integers are closed under multiplication, claim, formal, all that kind of stuff. All right, we have time for one more quick one. So let's say claim. The integers are closed under division. What does that mean? That's one of those things where it sounds, this is like something I'd read in a textbook and my mind would just go over and over it again. Like it sounds simple enough. You read it and go, oh, okay. Wait, what? What does that mean? What's it mean for the integers to be closed? What's it mean for a set to be closed under some operation?
Does it mean like we can take any two integers and just divide and divide and divide and we'll stay within the integers?
Exactly. That's exactly what it means. Like saying, like, if you have set S is closed under an operation, let's call it star, means for all X in S and Y in S, X star Y is in S. It's closed in the sense that you can't get out of S by just dividing or just using this operation. So my claim is that that's true for the integers. What do you guys think? True or false? Actually, let's first write it formally. So formally, what I'm saying here is for all X and Z and for all Y and Z, which is the integers, X over Y is in Z. Aside, what do we think? I mean, for example, 4 is in Z, 2 is in Z, and 4 over 2 equals 2 is in Z. So there's definitely some integers that you can divide and get other integers out, but is this true always?
No.
No.
Give me an example.
2 over 3.
Any
2 over
odd
3.
integer with 2.
What?
Any odd integer with 2.
Yeah, exactly, right? So 2 over 3 is not in Z. Any odd integer like 17 over 2 is not in Z, etc. Right, so we found these examples. So to disprove a universal statement is really easy. Just find an example. So I'll say proof. Or disproof, actually. Disproof. Let X equal 2 and Y equal 3. Now note, whenever you're doing an example or a counterexample, the first thing you have to do is, so the negation, this is the thing we're proving. The negation is there exists an X and Z, and there exists a Y and Z, such that X over Y is not in Z. All right, that's what we're trying to prove. Or that, like, to disprove means to prove the negation. So that's what we're proving in the disprove. So the point is we're trying to find an X and Y that's in Z. And so whenever we do that, we kind of make a claim like let X equal this, let X equal 2 and Y equal 3. We're defining X and Y to be this, but to start off, to show that we're actually proving this negation true, we need to first just explain why our example actually is in the domain we want to be in. And this time it's easy because we can assume, like, we're in this class, we're allowed to just look at integers and say that's an integer, right? But, you know, if there was something with rational numbers, we have to make some argument of why it was a rational number. Or if there was a claim about even numbers, we have to make an argument about why our numbers are actually even. So let x be 2 and y equal 3. Note 2 and 3 are even as required. Then I'll say, however, x over y is 2 over 3, which equals 0.6 repeating, is not an integer. Thus, there are integers, mainly x and y, such that x over y is not an integer, so claim is false. Any questions? So what's easier to prove? Universal statement or existential statement? I'm sorry. Is it easier to prove a universal statement or disprove a universal statement?
Definitely disprove.
Definitely disprove. Which one's more satisfying?
Prove.
Prove, right? Thank you. And by the way, disprove is easier to write, but sometimes it's actually harder to do because it requires you to find an example. And this is kind of an easy example, but when you're getting into high-level math and there's claims, the claims that exist are probably not obvious. People don't know if they're true or false, right? And so there might be a disproof that's just really hard to find, like a needle in a haystack. And so sometimes it is easier to prove something than disprove it. If you're trying to prove something, it's kind of like something only has a few properties. And you're trying to combine these properties in a certain way to get to your result. But to disprove, it's like, okay, here's the infinitely many integers, find the one that fails. That could be harder. But anyway, what time is it? 3:30. That is class. A little teaser for next time on Thursday. Yeah, exactly. On Thursday, well, that's true. You're right. That guy that disproved, theoretically though, maybe that it took that guy more than 300 pages of work to find the disproof. But then once you found it, you had to write it down. But anyway, a little teaser for next time. We'll prove the digits of any 4-digit multiple of 3 sum to a multiple of 3. That's pretty cool. But yeah, that is class. Have a great day, everybody. Thanks for showing up. Anyone have any questions? Anyone have anything? Like, anyone have anything they want to be proved? Like, they have an idea they think is true, and they want to see if I can prove it. Show you the power of math, like some sideshow act. If you do, email me. We'll talk about it. And don't give me like the Raymond Zeta hypothesis or something like that. But yeah. Thanks, everybody.
Thank you.
Thank you.
Oh, Trevor, thank you. Maybe see you in the review session tonight if you have any questions, or if not, Thursday or whatever. Yeah, thank you, Benay.
Bye.
Bye.